welcome and thank you for joining. Let's continue with example number 3. Recall that in this lesson we are exploring how to use the first derivative to graph the equation of a function. Now in this case we are given the equation of a rational function and asked to find where in the domain of this function is g of x increasing and where it's decreasing. In other words, we're asked to find the intervals of increase and decrease. And to find the intervals of increase and decrease, we use the first derivative. Remember that we reinforced in this lesson, at the beginning of the lesson, that a function is increasing in an interval where the first derivative is positive, and it is decreasing in an interval where the first derivative is negative. So what that means is that we need to find the first derivative. So we'll start off by differentiating this function. Now remember, this is a rational function, which means to differentiate it, we need to use the quotient law. The quotient law states that if a function is in the form f over g, then the derivative of it will be f prime g minus g prime f over g squared. So in our case, we have g prime x equals the derivative of x, which is the derivative of the numerator, equal to 1, times x squared minus 4 times the denominator, and then minus the derivative of the denominator, which is x squared minus 4. So the derivative of denominator would be then 2x, and then multiplied by the numerator. The denominator will be to the power of 2. So x squared minus 4 squared. Let's simplify this. So we have x squared minus 4 minus 2x squared divided by x squared minus 4 to the power of 2. Simplify some more, and we get negative x squared minus 4 divided by x squared minus 4 to the power of 2. Now, remember that we are trying to study the sign of the derivative, and when the derivative is in rational form, like ours, then both numerator and denominator will have the same power to change the sign of the function, or the same influence, so it will contribute to the sign of the derivative equally. So what that means again is that we need to study the signs of both numerator and denominator and then combine them together to get the sign of the derivative. So to determine the sign of an expression, we need to start off by finding the zeros of it. So for the numerator, we have negative x squared minus 4. We'll make that equal to 0, which means that negative x squared must be 4, or x squared must be negative 4. Now, as you can see, this is not possible, which means that there are no zeros to the numerator. Now, let's think a little bit about this. If there are no zeros to a numerator, which, by the way, is in quadratic form, and by the way, again, whose graph is in parabolic shape, so it goes either this way or this way. Now, we must be thinking now, why doesn't this function have zeros, A, and B, then what is the sign of this expression? So, graphically speaking, we're going to say that if a parabola has no zeros, then either the parabola is opening up without reaching or without touching the x-axis, or opening down without touching the x-axis. So these are the two different cases. Obviously, the parabola can be anywhere above or below the x-axis. Now, a parabola that opens up will have a positive leading coefficient, opens down a negative leading coefficient. And as you can see in here, our expression is a quadratic with a negative leading coefficient, which means that in our case, we're going to have a parabola that opens exactly this way, down. So when you think about the sign of this expression, then as you can see, based on the location of the graph, which is all below the x-axis, then the y values of this expression, which are made of all the values of this entire expression here, then are all negative, which tells us that negative x squared minus 4 will be negative from negative infinity to positive infinity, so for any real number x. Now let's study the sign of the denominator. So in the denominator, we have x squared minus 4 to the power of 2. So we'll study the sign of x squared minus 4 by making it equal to 0. And as you can see here, we get x squared equals 4 or x equals plus or minus 2. So these are key values that we're going to need to use in order to determine the sign of the denominator. So we're going to use this little chart here to determine the sign of the entire derivative. So the red line here represents the number line. So I'll place in here the negative and positive infinity. And the two key values that we just found, which are at x equals negative 2, positive 2. Again, they're not to scale. They just have to be placed in order. Now, for the sign of the numerator, I'll write the numerator in our case was negative x squared minus 4. And the sign of the denominator will be made of the expression x squared minus 4 raised to the power of 2. So at negative 2 and positive 2, we'll have the denominator equal to 0, which means that these will be zeros of the denominator. So I will align the zeros with the denominator. Numerator has no zeros, so there is nothing to place in there. Now, as we discussed before, this parabola here, or this expression, will always have negative values. And we explained this graphically. Now, what happens if, we're not visual, so we want to understand things logically or algebraically? So all we have to do is pick any number on the number line in order to study the sign of this expression. So remember that if x is, let's say, for example, equal to 0, negative 0 squared minus 4 will be negative. If x equals negative 100, so if you have a negative number raised to the power of 2, that will be positive, and then with a negative in front of it, negative, so that will be negative. And numbers 2 and beyond will also give this expression a negative value. So if you have 1 million in here to the power of 2, okay, there is not enough room for 1 million, but you get the idea. So then we're going to have an expression of negative sign. Now, for x squared minus 4 to the power of 2, now this is a unique kind of expression in a way. Now, the truth is that x squared minus 4 on its own will be negative between negative 2 and 2 and positive outside it. And that is because x squared minus 4 is a quadratic that opens up with 2 zeros. However, because this expression is raised to the power of 2, and I'm going to make this power of 2 a little bit more pronounced because it deserves it. So that will give the entire denominator a positive value. So the value of the first derivative then would be found as the product of the numerator, as the ratio of the numerator with the denominator. So we are going to say that a negative divided by a positive will give a negative. So a negative by a positive, again, it's the same idea, a negative and a negative. So what that tells us about the behavior of the function is that the function will be decreasing some more, and decreasing again. So in this case, we're going to say that this function is decreasing at all times. Now, we are wondering what is happening exactly at these 2 points where the denominator was equal to 0. So let's discuss the first derivative first. So at x equals negative 2 and positive 2, which are the zeros of the denominator, this derivative expression will be undefined. So we're going to say that the derivative is undefined. Now, if you look at the equation of the function, notice that x equals plus and minus 2 are also restrictions on the graph of the function, and we are very familiar with this concept and this idea because we have graph rational functions in the advanced functions course, and we know what is happening there, a vertical asymptote. So now I want us to think of one thing together. So if a function has a restriction at a point, these restrictions will be carried over to the derivative of it. So there will remain restrictions for the derivative as well. Now, that is the analysis that I wanted us to go over here with function gx equals x over x squared minus 4. So we have to state the restriction on the function itself. So we're going to say different than 2 and different than negative 2. So the restrictions on the derivative are also the same. So the shape of the graph at the restricted values will be or the graph will present a vertical asymptote, one at x equals 2 and another vertical asymptote at x equals negative 2. So, in conclusion, we're going to say that when the derivative of a function and the function itself have restrictions at the same points, then the graph of the function will present a vertical asymptote. We're going to take a look at other examples as well, where we see that the function has no restrictions, but the derivative does. And for this, we're going to take a look at example number 4. So you'll hear from me soon, so you check the next videos that are coming up. And thank you for learning with me. Bye for now.